Here's another interesting question from the Romanian National Olympiad from 2024. This was a ninth grade question, so it was given to students who were in ninth grade. And it was problem 2. And problem 2 actually had, I believe, 4 parts. So there was A, B, C, and D. But for this video, I'm just going to look at the first 2 parts, and maybe I'll make another video where we'll look at part C and D. And if you have any suggestions for any questions from Olympiads that you'd like to see on the channel, let me know in the comments. So let's read the question. It's titled The Rebel Toy Car for some reason. So it's given that we have a remote control toy car with mass M, which moves along a circular trajectory of radius r on a horizontal surface, which is part of the floor of a wagon. This is going to become relevant in part B. The coefficient of static friction between the car's wheels and the surface is mu, and we also know the gravitational acceleration, g. So we don't actually know any number, so this is one of my favorite types of problems because we can work symbolically, and the final answer is going to tell us the exact relationship between all the variables. Anyway, so for part A, we have to find the expression for the maximum speed of the car for it to describe a circular trajectory of radius r, assuming, for now, the wagon is stationary. And this maximum speed of the car has to be a function of mu, r, and g. So I'm going to use 2 approaches. I'm going to use one approach for part A, and I'm going to use another one for part B. So for part B, we're going to make use of Euler's equations, which are arguably the most useful kinematic equations that you can use in physics. And we're going to make use of them in part B, although you don't have to, but I think they're probably the most rigorous, they give you the most rigorous approach to a problem like this. And for part A, we don't have to, I don't think we have to go that far. We can do it in a more intuitive manner because it's relatively straightforward. So I'm gonna draw a circle. I'll try to draw a circle. And this circle is going to be essentially the path of the rebel toy car. Okay, so we've got the center of the circle is here, and it's got the x and y axis, which we're going to put in the center, and the car is going to move around the circumference. So at some point the car is here, and let's say that it's describing an angle phi with the x-axis. So let's try to understand what kind of forces are acting on the car in this moment. So the car has to be in uniform circular motion, which means that there is no tangential acceleration. But there is normal acceleration, and there has to be normal acceleration. In this case, it's also called centripetal acceleration, and we can use the formula v squared over r, and that centripetal acceleration is acting towards the center of the circle like this. And then the force that produces the acceleration, well, it's the centripetal force, but in this case, the centripetal force, the only thing that it can be is friction. So I'm going to call this Ff for friction. And we know that the friction is going to be equal to m times a, or an, let's say, in this situation. So this is the only, well, it's not the only force. There's also weight and normal reaction force, but they cancel each other out, so we don't really care about them. So we have that friction is equal to mv squared over r. Now we're asked to find the maximum speed of the car. So obviously if this car is trying to speed up too much, it won't be able to stay on the circle because it will start slipping. And it will start slipping when the friction is going to get, when the friction becomes kinetic. Because right now, even though the car is moving, this friction that is acting is static friction. So if you kind of try to look at what happens to the wheels of the car, so this is the wheel seen from the back or from the front. Let's say from the back, and let's say that the car is traveling like this. So we're gonna have that the friction is gonna act this way, right? So those two arrows added, well, there's 4 wheels, but I'm looking at the total friction in this case. So if the friction becomes kinetic, then it means the car is going to start sliding towards the right, which we don't want. So we want the friction to be static, therefore we want this to be less than the maximum value of friction, which we know is mu times n. So in other words, we have mv squared over r is less than mu, and n is just mg in this case. So we can cancel the m's. So v is less than square root of mu gr. And that's it. So that's part A, pretty straightforward. The velocity of the car in this case must not exceed this value, otherwise the car will start slipping to the right. And we get 0.6 points for this. Now part B is slightly more tricky, and we're gonna do it in a way that we can really understand what's happening. So we have to find the expression for the maximum speed of the car. Okay, we've already done that in a different scenario. For it to describe a circular trajectory of radius r, if the wagon moves with constant acceleration a, and we still have to do it as a function of mu, r, a this time, as well as g. So essentially what's going to happen is that this circle is going to move one way or another. And I'm going to say that, you know, the initial center of the circle is here. So this is where my coordinate axes, which are linked to the stationary, to the inertial frame of reference, are going to be. And then I have my the center of the circle at this position, let's say, which, not sure why I made it into a dotted line, but we'll just go with it. Actually, I don't really like how this circle looks, so let me try again. So I have the center of the circle there, and then, okay, this looks a bit worse, but we'll go with it. I'm gonna call this coordinate system x prime, y prime, o prime, like this. And in this case, this coordinate system, I'm gonna make the coordinate system essentially accelerate. And the car at this point, let's say it's gonna be somewhere here like this. And this is gonna be the radius. And what I'm going to do now is I'm going to write the acceleration of the car, a, in terms of the, well, using Euler's equations basically. So I'm going to say that the acceleration a with respect to the inertial reference system is going to be equal to a0 prime plus, we're going to say, alpha. So I'm going to use the full formula for now. I have this. We also had this. We also had the Coriolis acceleration, which is this cross product with the relative velocity plus relative acceleration. So, you know, it may not be necessary to go this far, but I just want to try a different approach, which is what I think this is the most rigorous approach for this kind of problem. I think at this stage, most students who are in ninth grade, they may not really be aware of this, but if they would, this would give them a massive advantage in those kinds of situations. Now, thankfully, a lot of terms will cancel. So this will cancel because there's no angular acceleration of the car. There is also another thing we can cancel, I believe, is this. And on top of that, we can also cancel this. Because omega is, or would be, the angular velocity of the second coordinate system, which we're not making it, we're not causing it to rotate in this case. So we have that the acceleration of the car is going to be equal to the acceleration of the non-inertial frame of reference plus the relative acceleration of the car with respect to the non-inertial frame of reference. So this turns into the acceleration of the non-inertial frame of reference, and this is the acceleration of the car with respect to the non-inertial frame of reference. I don't know if this is a standard way to abbreviate, but I'll just leave it. So the absolute acceleration of the car, therefore, is going to be equal to, now I'm going to say, for example, that this is this floor of the wagon is accelerating, you know, in the north direction or whatever. I'm going to call this A0. So this is going to be A0 times J. You know, it doesn't have to be in this direction, but it also doesn't take away from the generality of the problem either. And also, the relative acceleration is going to be equal to, so this is going to be minus omega squared r. Okay, and now we just have to figure out what r is. So we have minus omega squared, and r, or the r vector, is given by its two components. So the first one is r cosine phi times the unit vector I, and then plus r sine phi times unit vector j, like this, which gives us that the absolute acceleration is going to be equal to minus omega squared r cosine phi of I, and then I'm going to say plus j times a0 minus omega squared r sine phi. So what we got here actually is an expression for the acceleration of the car at any point along its trajectory, and the fact that it's at any point is quantified by this angle phi right here, which we're going to deal with in a bit. So let's think what forces are acting on this. Well, clearly there's weight, but we don't care about weight because the weight and the normal reaction force, they will cancel out. And then there's friction. So basically all this acceleration of the car happens because of friction. So we say that MA is equal to minus omega squared r, actually let me change this, let me put m first. So it's minus m omega squared r cosine of phi times I plus j, and then we have m a0 minus m omega squared r sine phi, and this is purely the friction. Yeah, so we can actually, doing it like that, we can actually get away from actually drawing the free body diagram. So I mean, we can if we want, but I'll just try to solve it in this way for now, because this gives us the friction as a vector, and this gives us the components in the x and the y directions respectively. The approach is going to be similar to part A in the sense that the magnitude of the friction has to be less than the maximum value. So we must have this less than the maximum friction, which is mu times n, which in this case is just mu mg. So the friction, or the magnitude of the friction, we can find it by calculating the magnitude of this vector. So in other words, we're going to get that m omega squared r cosine of phi squared, and this is going to be plus, and then we have m a0 minus m omega squared r sine phi squared. This should be less than mu mg. Okay, so what's left to do here is to solve this, we have to square everything up, and we are going to do that. And I think I would like to change my omega, I think, to v, but I'll do this in a bit. So I have m squared omega to the 4 r squared cosine squared of phi, and then we expand the second bracket, so we have m squared a0 squared minus 2m a naught, and then m omega squared r sine phi plus m squared omega to the 4 r squared sine squared of phi, and this is less than mu squared m squared times g squared. Okay, so the first thing that happens is that the m's go away from all the terms, like this. Another thing is this term and this term, they can combine and just get omega to the 4 r squared. So let's write that. So we have omega to the 4 r squared, and then we have that second term, which is 2 a0 r, and then omega squared sine of phi, and then we can write this as a0 squared minus mu squared g squared less than 0. Okay, so we keep having this inequality here, but what I'll do instead is I'm going to remove the inequality and I'm going to replace it with an equality and make this equal to 0. The reason for that is because I want to find the actual, critical velocity, which gives me maximum frictional force, which causes slipping. So, but before that, I want to change my omega. So we know omega is v over r, so we can actually do something here. So this first term is going to become v to the power 4 over r squared. Then this is going to be minus 2a naught, and I believe this is going to be v squared over r sine phi. And I think that's it. I'm going to put this in a bracket like this, and that's it. Okay, so the next thing I'll do is try to solve this for v squared. So this is a quadratic equation, right? It's a quadratic in v squared, so I'm going to find the discriminant, which is 4a0 squared sine squared phi over r squared minus 4, I have a0 squared minus mu squared g squared times 1 over r squared, like this. Okay. Let's move this to the next page and see what we can do here. So I think that we can factorize some things. So we can do 4 over r squared. I think this is the only thing that's common everywhere. And this gives us a0 squared sine squared of phi minus a0 squared plus mu squared g squared. We can use some trigonometry here, and this is going to give us, so I'll start with this, and this is going to give us minus a0 squared cosine squared of phi, like that. Okay, now for this to have solutions, this must be non-negative. So if we try to see what that means, so that means this should be non-negative, which means that cosine squared of phi is going to be, or should be, less than mu squared g squared over a0 squared, and then we can take the square root of both sides, which gives us that cosine of phi can be less than mu g over a0. Okay, now this has to be true actually for so okay, what I'm doing is I'm assuming that my cosine of phi is positive in this case, and this has to be true for all values of phi, and we don't really care about this being negative because we know that mu g over a0 is positive, so we only care about this inequality when the cosine itself is positive. So if this has to work for all values of phi, it has to also work for the highest value of phi, which is, or I should say, it should work for the maximum value of cosine of phi. I mean, so if cosine of phi is 1, which is the highest value, it means that 1 must be less than or equal to mu g over a0, which means that a0, which is the acceleration of the wagon, has to be less than or equal to mu g. Yeah, so this makes sense because otherwise, if the acceleration is higher than mu times g, then the car won't be able to not slip, essentially. So we're going to keep this in mind, and we're going to try to find what v squared is, therefore. So we have this nice quadratic here, which we're going to make use of in a second. So I think this one was r squared, and we found a discriminant. So v squared is going to be equal to 2a naught over r sine phi plus or minus, and then we have square root of the discriminant, which is this basically. So that's 4 over r squared, and then we have the stuff in the brackets, so mu squared g squared minus a0 squared cosine squared of phi, and this is divided by 2 over r squared. Okay, 4 over r squared actually can come out and becomes 2 over r, and then we cancel out some things, so we cancel out the 2's, we cancel out this, this, and this, and we get that v squared is going to be equal to r times a0 sine phi plus or minus this. So let's talk about this for a second. We have found what the maximum velocity is, but we found it in terms of the angle phi. And this kind of makes sense because that means that at each position, so for each angle phi, the car is going to be able to experience a maximum frictional force. So I'm going to make a diagram, which is not going to be very accurate most likely, but it's going to convey the idea pretty well, I think. So as the car is rotating, and it's also accelerated, so it's not really rotating, as it moves along this path, it will experience different values of maximum frictional force it will be able to experience different values at different positions. So let's say that the distribution of the frictional forces look like this, which looks like some kind of MRI scan, but anyway. So let's say that when it's at those positions, when it's like top and bottom, right? It will be able to experience, it will be able to take a large amount of friction. When it's at the sides, it will only be able to take a small amount of maximum friction. So to be able to experience the same maximum friction everywhere, what does that actually mean? Well, we can't actually take the maximum, which is here, because that value is not going to be withstood at the other points. So instead what we have to do is we have to take the friction, the maximum friction which occurs at those points, because this is, if you do that, this is definitely going to be able to be withstood everywhere. So yeah, so we have a different velocity we have different velocities, different maximum velocities for different angles, and out of all of them we should take the minimum one, because the minimum one is guaranteed to work everywhere. You can't take the maximum one, because the maximum one only works at here and here, but nowhere else basically. So we have to minimize this function, and you can actually do that, and the best way to do it is to differentiate. So if you do dv or dv squared by d phi, and you equate it to 0, you'll notice that what you'll get out of it, and I'm not going to go through the steps, but you can try this yourself. You'll get that the answer is going to give you that cosine of phi should be equal to 0. So if cosine of phi is 0, then this will give us our answer. This will minimize the value of v, or the value of v squared. So let's think what that means. So if the cosine is 0, then the angle is either 90 degrees or 3 pi over 2, which is 270 degrees. So in other words, this phenomenon of the minimum out of the maximum velocities is either here or here. Now only one answer is correct, and we'll see which one in a second. So let's try to substitute. Let's try to use pi over 2 first. So we know that v squared, so let's say case 1, phi is equal to pi over 2. So v squared is going to be r times, so this is a0 plus or minus mu squared g squared, and I think that is it, which gives us that v squared is going to be r multiplied by a plus or minus mu g. And let's look at the two solutions. So the first one is when v squared is r times a0 plus mu g. This is not going to work because this is the maximum speed. Because when you differentiate, obviously you get stationary points. So now we're thinking which one is maximum, which one is minimum. So this one is clearly the maximum velocity, which is not what we're looking for. The other answer is r times a0 minus mu g. And although this looks okay on the surface, let's remember that a0 has to be less than or equal to mu g, or this has to be less than or equal to 0. And if that's the case, then this is less than or equal to 0, which doesn't work, because this is a quadratic. It can't be less than 0. It can only be 0, but if the velocity is 0, then nothing is happening. So we're not interested in that answer. So let's look at the second case. So the second case is when phi is 3 pi over 2. So at 3 pi over 2, if we substitute values in, we're going to have v squared equals r multiplied by a0 So sine of 3 pi over 2 is minus 1. And then we have plus or minus just mu g, right? Because cosine is 0, therefore we just have mu g. Case 1, v squared is going to be equal to r minus a0 minus mu g. This is clearly not going to work because this is strictly a negative number and we can't take a square root of a negative number and still get a real number. And the other case is when v squared is r, so this is literally our last hope. Minus a0 plus mu g, and this is good. So this is the minimum velocity, the minimum value of the velocity from all the maximum values, if that makes sense. So first of all, we put the condition for friction to be maximum, so we wanted the velocity to be as high as possible, but then we noticed that the velocities are dependent on the angle, so we wanted to choose a velocity that works that works at all angles, because the velocity of the car in the non-inertial frame of reference has to be constant, and it has to be equal therefore to this value because all the others don't work. Therefore the final answer is v is equal to the square root of r mu g minus a0. Obviously you can do this, by using some intuition, but for this particular question I just prefer to do it using Euler's equations for acceleration in this case. We had to deal with a quadratic. We had to solve this like min-maxing problem, and we got this result which looks relatively simple. And that's the end of the question.